Hello everyone, this is Ephira, the online page in which you can simulate your building and see how efficient it is in terms of costs and energy consumption. In this case, we upload a model of a floor that is in real life, that is in Guadalajara, to see how efficient it is and how the strategies will make it even efficient. At the first model is without any strats, and here we can see its consumption. But then we make models with different strats individually to see how they improve the building, and at the end we combine them to make our building 30% even more efficient. But how did we achieve that?
Well, now here we have our building, our model. We have established the first specifications in the envelope tab, the normal ones. We started at climate zone 1, and we have the 0.8 of solar heat gain coefficient, specifically in this, the C facade. We have concrete block walls, tiles floor. Well, as in infiltration type, we have crack infiltration and concrete in our roofs. Then we made 4 clones of the baseline concept. In the first one, we do the facade glazing changes. We change this just in the C facade. We decided to go for 0.25 because in the response curve, we noticed that is the best option because it's the one that is in the lower point in the graph. We can see it here as an example. I'm just gonna do this with this specification because we do the same thing in all the clones and different things that I'm going to explain, but I'm just going to run the simulation of the response curve in this one because it's a little bit low, so a little bit slow, I'm sorry. And I forgot, we have to run it in the UI output, and we have to select less steps. Again, I'm gonna run this, and we're gonna wait. And when it is done, we can see here, let it finish. Yeah. And then the 0.2 part, we have the lower part of the graphic. So yeah, that's why we decided to put 0.25 in our solar heat gain coefficient. This is the same. Then we go to the clone B. We already run the simulation, so we're gonna go to this part and we're gonna see the override glazing radio. We have the same specifications here, and we decided to put 0.2 in the C facade because we changed it in our response curve that we had to run here from 0.2 to 0.9, and that's why we decided that. We jumped the clone C because we didn't have to change anything in our building orientation. Then we have the software shading. All of the specification are the same that in the first one, and we decided to change some things here, but just in the C facade because it's the part where we are receiving sunlight. And we just use horizontal shading and go for 0.25 horizontal shading because of the response curve that we already run, and we found out that in the graphic this is the better point, so we decide to go for this. And finally, in the clone E, We change everything to these specifications that we already have. Here we have in the facade C the point 75 in the C facade, and here we already have in the override glazing we just changed this one, the 0.77 facade, the window to a radio. Here in facade glazing in the C, we have 0.25 as in here. And that's it. We run our simulation and we can see that we have this. It has reduced a lot from 152 to 118. And then we can see here in the energy breakdown which is a graphic that shows us how we have reduced the systems. We want to compare concepts and see just the cooling part. Here it's the blue one, and we can see that from here to here we have reduced this 37% of the cooling energy. So that's it in our model, and that's how you do it.
So we made an Excel to calculate the envelope cost of our 33 stories high office building, where we had the goal of having the maximum energy efficiency possible. For the linear meter of facade solar protection, we calculated by multiplying the area of our window that they have dimensions of 4 meters high and 38 meters long times the window to wall radio times the facade solar protection. For the south facade, we multiply the area of 152 square meters times our 0.2 window to wall radio times the cost of 30,000 of facade solar protection. The final cost, taking the whole building of 33 stories high for this facade, is 30,096,000. For the north facade, we did the same procedure as the south facade with a change at the 0.8 window to wall radio, and that gave us a total of 120,384,000. For the second part of the assignment, we calculated the insulated wall for both facades. For the south facade, we multiplied the area of 152 square meters times the horizontal shading of 0.75 times the window to wall radio inverse of 0.8 times the cost of the insulated wall of 10,000. The final cost, taking the whole building, was 3,096,000. For the north facade, we did the same procedure as the south facade with a change at the 0.2 window to wall radio inverse, and that gave us a total of 7,524,000. The last part of the assignment, we calculated the override glazing for both facades. For the south one, we multiplied the override glazing of 0.77 times a clear glazing of 0.85 that costs 10,000, and that gave us a final cost within the 33 stories high building of 254,100. For the north facade, we multiplied the override glazing of 0.77 times a mild protection of 0.40 that costs 20,000, and that gave us a final cost, taking the whole building of 33 stories high for this facade is 508,200. And last, our grade total was 188,862,300.
doing the Excel, when we wanted to calculate the cost of the building, we noticed that it was very expensive because of the glass that we decided to put. For example, here in the north facade, we decided to put the glass with 0.8 solar heat gain coefficient, and that is a glass of $10,000. But in the south facade, we decided to put a 0.25 solar heat gain coefficient, which is the $5,000 glass, and that increased our price a lot. So we decided to change it to 0.4 in the solar heat gain coefficient, which is the $20,000 glass, and that it was gonna like make our building cheaper, but it was important to not increase this number too much, because we don't want that. We want to make a balance, so it's efficient but also cheap, or well, not too cheap. I mean, a balance in the price and in the energy that we use. And yeah, it's okay because it just increased one number. And here in the energy breakdown, the graphic, when we compare concepts, we can see that the percentage, well, we have to see it in the baseline concept, the percentage, it was 36%, and it remains the same. So it's okay, we can change our glass and it's cheaper, and it doesn't affect our energy efficiency.